Page 93, we've been talking about the makeup of atoms, looking at different elements. Yesterday we spent quite a bit of time talking about atomic numbers, atomic mass. All that came off of the Crookes tube experiment where the corpuscle, later renamed as the electron, was discovered. The electron, that small, negatively charged component of the atom. Remember, prior to this, the idea was that the atom was indivisible from Dalton. We had that theory. Now that idea has just been shattered because here's a piece that's coming from atoms. It's a piece of an atom. Therefore, the atom must be able to be destructed because we have pieces of it coming off. How do we understand that? And the result of that was the plum pudding model of the atom, where for our ears, for our custom, the blueberry muffin model of the atom, where the cake was considered to be positively charged and the electrons, being the fruit in the muffin, were considered to be negatively charged. That was the best model they had at the time to try to figure that out. We spent some time yesterday looking at each of the different elements and saying, okay, we know that there are components known as electrons, protons, and neutrons. We're going to talk a little bit today about how some of those were discovered. But given that there are electrons, protons, and neutrons, each element has its own particular unique number of protons. It's the proton that determines what element that atom is. Its identity comes from its proton count. Also electrons, and we've said that the atomic number, which represents the number of protons, also represents the number of electrons in an electrically neutral atom. It's not an ion, it's an atom, a neutral atom. So by definition, it has the same number of negative charges as positive charges. Remember, a few days ago we said that everything has charges. The question is whether or not the positives and the negatives balance each other out. And if they do balance each other out, the whole thing has a net zero charge. It's neutral. If there's one more positively charged particle, then the whole thing is +1. If there's one more negatively charged particle than positive, then the whole thing has a net -1 charge. So for an atom, it has, sodium, for example, has 11. Atomic number is 11, meaning it has 11 protons, and it has to have 11 protons. It will have 11 electrons if it's a neutral atom. If it has 12 or 10, then it's an ion. But it's still sodium. And then lastly, we talked about neutrons. The neutrons are those neutrally charged particles that we see up here, and we get that information from the atomic mass number. The atomic mass number represents the number of protons and neutrons combined. So if we have the mass number and we subtract the atomic number, that'll give us the number of neutrons. However, that number from most charts is not an even integer number. It's not a number like 10, 11, 12. It's some funky stuff like 132.905. You're saying, well, how can I have a fraction of a neutron? So remember that the atomic mass is an average, that atoms of one element can actually have differing masses between them because they can have a different number of neutrons and still be that same element. Using sodium again, every sodium atom has to have 11 protons. Every sodium atom will have 11 electrons if it's neutrally charged. But there are differing numbers of neutrons for every sodium atom. Not every one, but there's certain numbers you can have. In this case, 22.98, which lets me know it's really close to 23, which tells me that on average, sodium has 12. Sometimes it has 11, but mostly, predominantly, it has 12. Because 12 and 11 would give me 23. The number up here is 22.98977. Really, really, really close to 23. Okay. Well, how did we come up with these numbers? We're going to talk about moving from the plum pudding model onto the Bohr model in just a moment, but there's a section here which is kind of interesting. It kind of stands off on its own because a lot of people find it interesting, and that's about nuclear bombs. And so we're going through this making up of the atom. Boom, let's talk about nuclear explosions for just a moment, then we'll go back to the makeup of the atom. Notice on here that they talk about, and we talk about today because of the world that we're in, this desire to keep not only nations, but some rogue or some terrorist organizations from getting nuclear weapons. And the major point that's being made in this whole section, the predominant the major portion of this whole page on page 93, is that making an atomic bomb is incredibly easy. If you want to get plans for one, just Google it. It's easy to make an atomic bomb. It's incredibly difficult to get the fuel that you need to fire off an atomic bomb. So when you hear about keeping nuclear technology away from countries, it's not really the technology that's the secret. It's not the bomb itself. It's not the casing and the mechanism and all this other stuff in the bomb that's hard to make. And I don't know if that makes you feel better or worse, that you guys right now could go out, get plans, and build a nuclear bomb if you wanted to. But you'd have a hard time getting the fuel that you need to actually explode the thing. And that's where the technology, when they talk about the technology, that's where the secrets are at. And how do you get the fuel that you put in the bomb to make it go bang? Because you'll notice on here that they talk about this idea of radioisotopes, and uranium is what's used in the first paragraph break down the page. It talks about uranium, and uranium is the usual fuel that's used for nuclear bombs. However, uranium has 3 different isotopes. U-238, see, 238, 235, and 234. See, I can write this now, and you know it's uranium, 238, 235, and 234, meaning for it to be uranium, what kind of atomic number are we looking at? I'm not quite sure where uranium's at. 92. Right here, atomic number 92. So we've got 92 protons. Atomic mass of 238. Well, actually, 235 is the one that goes boom. Okay, looks like a tree, could be a mushroom cloud. Okay, 235. So how many neutrons are in uranium-235? Well, we've got 92 protons. So 235 minus 8 less than 100, right? So it'd be 135 plus 8, 143. There's 143 neutrons and 92 protons in uranium-235. This right here is the fuel. Uranium-235 is the fuel that you need for the atomic bomb. But you'll notice on there that they tell you that uranium-238 is 99.3% occurrence. 235 is about 0.7% occurrence, and 234 at 0.01. Okay, so if I have 100 uranium atoms, the chances are that I don't even have a uranium-235. If I have 200 atoms of uranium, I've got a 1.5%, 1.5 maybe, so it's still less than 2. Let's make the numbers really big. If I have 1,000, okay, my chances of having a uranium-235, out of 1,000 atoms, I only have 7 that are actually 235. So I've got 7 atoms out of 1,000. So if you think about nuclear bombs, it's kind of like a car. Let's say that a car was easy to make, but there was no gasoline. Kind of like a Mad Max world, right? There's tons of cars, there's no gas. So you can't run any cars because there's no gas. It's easy to make a bomb, but you can't get the fuel to explode the bomb. The technology secrets are how do we get uranium-235 enriched enough, and that's it, isotope enrichment is what it's called, to get enough uranium-235 that there's actually enough stuff there to explode. That's the real secret. They mention in here the Manhattan Project. The Manhattan Project during World War II is when our scientists figure out how to do this. And it's been a closely guarded secret since that time. Now, other nations obviously know how to do it, but everybody that has it knows that this is the key, how to get from 0.7%, we've got to get that up to about 7%. So we have to 10 times enrich that to get it to 7%. And once we get it to 7%, then we got something that might actually go bang. All right. So 235, uranium-235 is the fuel we need. Naturally occurring, it's about 0.7%. Process of isotope enrichment to get it to be about 7% of the sample. Once we have it at about 7% of the sample, then we have enough material that we can put into the bomb that we could make over the weekend by Googling the instructions, and boom, set it off. See, up until this point, uranium-238 versus 234 versus 235, it wouldn't have had any meaning. So we had to discuss what it means to have a neutron, how to figure out how many they have, how the same atom can have different types or different numbers of different numbers of neutrons, so we can even approach the idea of enriching it to make the fuel. Obviously, it's beyond the scope of this course to explain why we need 7% versus 0.7%, but hopefully that's good enough. That's sufficient. All right, so now we jump back from bombs back to plum pudding. How's that? J.J. Thomson and the plum pudding model. And at this time, Rutherford was also, Rutherford was a student of Thomson's, and Rutherford was working with what he called alpha particles. Again, they named these particles alpha particles, beta particles, by these Greek letters because they don't really know what they are when they first discovered them. All he knew was, when I've got something that's radioactive, it's emitting these particles. Radioactive decay emits certain particles. Let's call them alpha particles. And let's see if we can use them to figure out not only what they are, but what other things are as well. So he had alpha particles. He knew that they were positively charged and that they came out of radioactive elements. So on page 95, we're going to get into the Rutherford gold foil experiment. I do believe Tyler DeWitt has a video that talks through the alpha particle experiment. I haven't viewed it since last year, so I'm going to go ahead and do a quick summation on it. I know we've got about, actually we only have about 15 minutes, don't we? Okay. I may defer to Tyler for this. Let me check real quick, excuse me. Is everybody awake enough that we can risk turning off the lights? Would you wake up your partner and ask him if they're awake? All right, so as Tyler just told us, the real shocker for Rutherford was not, and his Rutherford gets most of the credit, if not all the credit, but he was part of a team. And these were all students, they were all students together working on this. And so of these three different models, how they developed, Dalton's, they had been involved. Their teacher had been the one that basically came up with the electron and said, you know what, Dalton's model of a completely hard and solid atom is wrong, that there are pieces, that an atom is made up of pieces, which created the plum pudding model. And so Rutherford expected everything to pass completely through. One other way to think of it too is that there's so many positive and so many negatives that as that alpha particle came through, that it would experience a net effect of zero. In other words, if we had somebody standing up here and somebody took one arm and somebody took the other arm and we just pulled really hard in opposite directions, if we pull the same amount, the person's not going to, well, unless they split, right? But they're not going to move. Like they're drawn and quartered. They're going to be there. If they're getting pulled equally in both sides, the net effect is nothing. That kind of a thinking is that if the alpha particles came through and there was positive and negative charges throughout, that not only because of the momentum of the alpha particle, but because the balance of charges they'd be being pulled in all different directions at the same time, so the net effect would be nothing. They'd be equally pulled to the left as pulled to the right, so they would go straight through. So the shocker for them was that, not that things went straight through, but that some things actually reflected or rebounded. That in that hoop that they had of the fluorescing material, that it sometimes that the alpha particles actually did come back in a way that looked like Daltons when they did come back, but the vast majority of them went straight through like they expected. So they got a combination response from their experiment, which shocked them. And the only way that they could explain all of that was to come up with a model of the atom. It's not as if they had a model of the atom, and then they went back and explained, and then they did an experiment that proved it. They did an experiment, and they got results that didn't make sense with the way they understood things. And because the way they understood things didn't make sense with the data they collected, they had to change the way they understood things. See? That's one of the problems in a lot of experiments is we believe we know what it's supposed to be. We do an experiment, we don't get what we think we should do, so we think we did the experiment wrong. We keep trying to come up with experiments to prove what we think we already know. As opposed to, hey, this is a legitimate experiment that we're doing. Let's try to understand and explain the results we're getting in a way that may not have been thought of before. Dalton's model was after, like, remember we talked about this, like 2,500 years of thinking. And then in a very short period of time, we went to the plum pudding model. And then in an even shorter amount of time, we went into the nuclear model. And as he alluded to, even this way of understanding the atom in the nuclear model like that is not the way we currently think of the model. Just as foreign as plum pudding is to this model, this is somewhat foreign to the way we're going to teach the construction of the atom later on in this very same module. But you need to understand this to be able to understand this, to be able to understand this, to be able to understand where we're going next. And even Tyler in the last presentation told us, or no, it was the crash course. Even our current understanding, one of the things we've learned is that every time we think we've got it figured out, we really don't. Every time we think we've come up with a model that explains it, some experiment's going to come along that's going to give us results that we don't quite expect. And though we may want to check our experiment to find out if we did something wrong, the real answer may be we did everything right and we need to tweak the current model. And so how we understand how things are bonded together. Is it because iron has hooks and clay has balls and socket? Or is it because of valence shell electrons? How is it that we say that like charges repel and opposites attract, and yet we have a center of an atom that's full of positive protons held together? Shouldn't they be repelling one another? Circled or having electrons all around them? Shouldn't they be attracted and just fall into the center? And wildest motion when things that should be repelling and attracting seem to be, things that should be repelling seem to be held together, and things that should be attracted seem to be held apart. What's going on there? Asking those kind of questions help us push to the next understanding of what the atom looks like, what it actually looks like, moving us forward. And that's why in Crash Course the encouragement that, hey, the answers to those questions aren't going to come from people that are in their 60s, 70s, 80s, and 90s. Eventually those folks, we're all going to die out. But guess what? The next wave of scientists need to come along and pick up the mantle and continue to press to figure out. And ultimately, what I think is really cool is ultimately, as we figure these things out, these are not just random pieces of information. They're not just statements of truth, but because of creation, because of our worldview, we believe that these, in a way, express the very nature, character, and purposes of God. So that's why a lot of scientists, coming from a Christian perspective, are engaged in science not because they love nature, but because they love the God of nature. Their interest is in the creator, not in the creature, because the creature reflects the greatness of the creator. As we study atoms, matter, electrons, neutrons, shell, valence theory, we're really, in a way, coming to understand God better. So kind of make chemistry into this big theology class, but it is. It really is. I'll see you tomorrow.